Good day, we'll discuss now solving word problems on logarithmic equations. So example number 1, it's all about population. So the number of ants in a nest doubles every month. If there are now 600 ants, about how long will it take for their number to grow to 9,600? And we are asked to use this formula or this model. So first is we need first to write the given. So we're given with the initial, so A sub 0 is our notation for the initial population. So initial population is 600 ants. The rate is 1 since it doubles every month. When we say it doubles every month, it means that 100% of the population doubles. No? 100% of the population doubles. So that is why the rate is 1. So 100%, the rate is 100%. Okay, but of course in solving we do not use the percentage. We use the decimal. So, or a number, a whole number which is not in percent. So we just divide the given, the rate, by 100%. So 100 divided by 100 is 1. So the rate is 1. And also, it is given that the final population is 9,600. So we will find the time t. Now, on how long will it take for these 600 ants to grow to 9,600, given that the rate is 100%, meaning they double every month. So let's start with this formula or model. So let's substitute. We have 9,600, A sub 0 or the initial is 600, and the rate is 1. And then we have this variable t for time. Now, of course, you cannot use logarithm here because the exponent t is only for this expression 1 plus 1. Okay, first we can do that 1 plus 1 is equal to 2. And then since we cannot apply logarithm because of the 600 does not include in the exponent t, so we must first divide both sides by 600. So cancel the 600. Okay, so take note t is only the exponent for 2. Now next, 9,600 divided by 600 is 16. And the other one, we are left with 2 raised to t because 600 is cancelled. So we can now use the logarithm. So take the logarithm on both sides. And then by law number 3, this exponent t will become a coefficient by law number 3. Okay, the exponent will become a coefficient. So now we have t log of 2. And then since we want t only, so we can divide both sides by log of 2. So we can cancel that. So therefore, we have log of 16 over log of 2. When you use your calculator, it is equal to 4. Okay, so meaning it will reach 9,600 if after 4 months, because our time here is in terms of months. Now another solution for this one is using the exponential method. So 16 is equal to 2 raised to t. Take note that 16 can be written as 2 raised to 4. So by one-to-one property for exponents, we have 4 is equal to t. Because they have now the same base. The base is 2. So by one-to-one property, their exponents are equal. So the same thing uh, will happen. So 4 months. T is equal to 4. Okay, now let's go to example 2. In t minutes, so meaning our time is in minutes, there will be f of t bacteria present in a certain culture, where f of t is equal to a sub 0 e raised to 0.03x. Okay. Now, if 60,000 bacteria are present initially, okay, if the bacteria present initially 60,000, after how many minutes? So we're asked to find time. Will there be 200,000 bacteria? So meaning since it's initial, that is our A sub O. Now every time we have a sub O in the model, it means it's the initial value. Okay? And of course, our f of t, okay, so our f of t is 200,000 bacteria. So this is the future number of bacteria. So the question is, how long will it take for the bacteria to grow to 200,000 from 60,000? Okay, so from 60,000 to 200,000, we are asked to find the time. So let's substitute. So f of t is 200,000. This is the final number of bacteria, or the future number of bacteria, which is 200,000. A sub 0, our initial, we have 60,000. And then we have here E. Okay, so we still have E there. So we can divide both sides by 60,000 first. We cannot apply logarithm because there is a 60,000 here. So we can cancel 60,000. So 200,000 divided by 60,000 is 3.333. And here we're left with e raised to 0.03 t. Now this time we can now apply logarithm. Now since we have here, this is the base e, so we will use the natural logarithm, so ln. So take the natural logarithm to both sides, on both sides of the equation. And then by law number 3, the exponent here will become a coefficient. So by law number 3. So 0.03t will now a coefficient of ln e. And then take note that ln e is equal to 1. Okay? ln e is equal to 1. So this is equal to 1. So meaning we're left with 0.03t. And then since we need t, we can divide both sides by 0.03. So divide both sides by 0.03. So cancel, cancel, and then you put this on your calculator, input that one. So the result is 40.132 minutes. For about 40 minutes, the bacteria will grow from 60,000 to 200,000. So the answer is 40 minutes. Example 3, it is determined statistically that a certain city t years from now will be f of t. So this will now our model. F of t is equal to 40,000 e raised to kt. This is now our model. And k is our constant. Now, if the population is expected to be 60,000 in 40 years, meaning this will be 60,000 and the time is 40 years, when is it expected to be 80,000? Okay, so now take note that we have two variables here, k and t, and k is not given. Okay, k is not given. So first, we need to find the value of the constant k. So for that, we will use this statement, 40 years and 60,000. So we'll start with that. So let us first the value of the constant k by using t is equal to 40, or 40 years. And of course, f of 40 is 60,000 because this is the population of in 40 years. So I have this. So f of 40 equals 40,000 e raised to 40k because our time here for this particular situation is 40. Okay, 40 years. Then divide both sides by 40,000. Okay, so 60,000 divided by 40,000 is 1.5. Okay, so 1.5. And then here we are left with e raised to 40k. Now, since this is the base is e, then we will use the natural logarithm. So ln 1.5 is equal to ln e raised to 40k. And again, use law number 3. The exponent will become an or a coefficient. So 40k will now be written here. And then ln e is equal to 1. So that is why we have here 40k. And then since we only want k, we divide both sides by 40. So cancel. So input this in your calculator, ln 1.5 divided by 40. And the answer is 0.0101. So this is only for the value k. We're not yet done because we did not answer the question when is it expected to be 80,000. So we only found the value of k. Okay, now we're now ready to find the value of t with f of t 80,000. So now for the last part of the solution, our new f of t now is 80,000. Okay, and our constant is 0.0101. So we need to find t. So take note, we already found k, so 0.0101 t. And f of t now is 80,000 because this is now the new population. Okay, but we need to find the number of years in order for us or for this 60,000 grow to 80,000. Okay, next. So we divide both sides by 40,000. Then after dividing that one, 60,000 divided by 40,000, again that is equal to, this is 80,000, okay? So typo error, that is 80,000. So 80,000 divided by 40,000 is 2. So here, cancel, we're left with this expression. So since this is E, meron tayong ln2. So ln2 is equal to ln E raised to 0.0101 t. Then by law number 3, so the exponent will become the coefficient 0.101 t ln E. And ln E is equal to 1, so we're left with this one, this expression, because ln E is 1. Okay, so this is equal to 1. So since we want t only, we divide both sides by 0.101. So using your calculator, we will arrive at 68.6 years. No? So after 68.6 years, we will arrive at 80,000. Okay, so the population will be 80,000. Okay, example 4. A certain town has a population of 16,400 in 1990 and 20,200 in 2000. When will the 1990 population be doubled? Okay, and we are asked to use this formula or model. Okay, take note that in the given, we do not have the value of r. So r is another constant. So just like the k from the previous example. So we don't have any r. So that is our first step. We need to find the value of r. So meaning when we find the value of r, dapat a sub o, and t are given. So in that case, we will use first this information. Okay? So 16,400 will be our initial, the a sub 0, and the future value for this particular time is 20,200. So as our future population A. And during this time, our time is 2000 minus 90. Okay? 2000 minus 90. So our time is 10. So substitute. Okay, our R is unknown, so we have the variable R. And again, divide both sides by 16,400. So cancel, cancel. So we're left with e raised to 10r equals 1.2317. Now, since this is e, so we'll take the natural logarithm on both sides. And then again, apply law number 3. After applying law number 3, now take note this is equal to 1. ln e is 1. So we divide both sides by 10 so that we're left with r. So input this on your calculator, ln 1.2317 over 10. Okay, so round off your answer to 4 decimal places. So we have 0.0208. Okay, now we have our R. We're now ready to solve for this question. When will the 90 population be doubled? So it involves 90. So meaning our initial population is still 90. So which is 16,400. But of course, our future population is this, be doubled. So meaning 16,400 times 2, we have 32,800. So the 90 population is now doubled. Okay, so 16,400 times 2 is 32,800. So our R was solved already. So R is equal to 0.0208. So substitute. We have this 32,800 is equal to 16,400 times e raised to this expression. Again, divide both sides by that. And then we have 2 is equal to e raised to this expression. Then again, natural logarithm. Since this is e, we'll take the natural logarithm on both sides. And apply law number 3. So law number 3. And then again, ln e is equal to 1. So that's why we have this. And then since we only need t, divide both sides by 0.0208. So input this on your calculator. We have 33.32 years. Now the question, when will? So from 1990 plus 33.32 years, we have 2023.32 years. But then 2023 is not yet finished. So we can say that by 2023, the 1990 population will double. No? Okay, so by 2023. Okay, let's go to our next example about depreciation. A cell phone worth 12,000 was bought T years ago. If it depreciates 5% per annum or per year, and its present price is 10,288.50, find T using A is equal to that expression. Okay, so here our initial price is A sub 0, which is 12,000. This is the initial price. And the final price now is 10,288.50. And the rate, our R for depreciation is of course 0.05. So 5% divided by 100%. Okay? So 5% divided by 100%, that is 0.05. So now let's compute. Let's substitute these values. Okay, substitute. And 1 minus 0.05 is 0.95. Then divide both sides by 12,000. So we have this value. Now this is not e, so we can take the logarithm base 10. So that is 0.95. So let's take the logarithm base 10 on both sides. And then apply law number 3. So t log 0.95. And then since we only need t, divide both sides by log 0.95. Okay, and then you input this on your calculator. You will have approximately 3 years. So if you substitute this, this is 2.99999. So approximately 3 years. So therefore, the phone was bought 3 years ago. So the cell phone was bought 3 years ago. Okay, last example, exponential decay. Now, half-life is the amount of time it takes for half of the amount of substance to decay. Now, the half-life of radium-226 is 1,620 years. Find the time required for 85% of 8-gram sample to decay. So 85% of 8-gram sample has been decayed. So we are asked to use this expression or model. Now take note, this one here is an exponent. So t over t sub 0.5, where t sub 0.5 is our notation for half-life. Okay, so let's label our a sub 0, our starting amount of the radium is 8 grams. Okay, now take note, 85% decayed. Okay, decayed. So it means only 15% will remain. So 15% divided by 100. So 15% divided by 100%, we have 0.15. So only 0.15 of the 8 grams. Alright, okay? So 15% of the 8 grams will remain. So that is why we have 0.15 times 8 is 1.2. Now find t in years. Okay? So here, our initial, we have 8 grams. And then since 85% of the 8-gram sample has been decayed or has decayed, then of course the final one, the final gram or mass is only 1.2 grams. Okay, and take note, this is an exponent. So we have 0.5. Our t is the variable, no, the years, the time. And this t 0.05 or 0.5, this is the notation for the half-life. Now, it is stated here that the half-life of radium-226 is 1620. That is why I substituted this 1620. So this is the half-life of radium-226. So again, this is an exponent. So here you cannot apply the logarithm first because we have 8. So let's divide both sides by 8. So we have 0.15 is equal to 0.5 raised to t over 1620. Now this time we can use logarithm. So this is not e, so we will use the log base 10. So we have here. And then apply law number 3. So this will become a coefficient. So t over 1620 times log of 0.5. Okay, now we need to cancel this. We only need t, right? We only need t. So meaning to cancel 1620, we need to multiply this with 1620. Okay, so that we can cancel this. And then we must divide log 0.5 so that this will be cancelled. And then t will remain. Okay, t will remain. On the other side also, we must multiply this one with the same expression to maintain equality. So 1,620 divided by log 0.5. Multiply it to log 0.15. So it will look like this. So it can't be seen here, but there is an expression there. So cancel na. So I will write it again. So 1,620 divided by log of 0.5. So cancel, 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 cancel. So we're left with t. Now here you multiply this, all of this. You input this on your calculator. So 1,620 divided by log of 0.5 times log of 15. 0.15, log of 0.15. So you will get an answer of 4,433.88 years. So this is the time required for 85% of the 8-gram sample to decay. So I hope you've learned something and thank you for listening.